All right, good morning and welcome to class. We're going to be working on example number 4. This is the final example in section 3.7, and as you probably remember, we're working on optimization, also known as finding maxes and mins. Let's do this in chunks. What I'd like you to do here first with this question is read it. I'll read it out loud here real quick. It says, a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 245,000 square meters in order to provide enough grass for the herd. What dimensions will require the least amount of fencing if no fencing is needed along the river? One of the things we mentioned last time is that every now and then a picture is a useful tool to use, and so I think it is useful here as well. So I'd encourage you to take just a minute here and try to draw a picture of this situation. So go ahead and pause the video and try that on your own, and then play it when you're ready to see the solution. All right, so based on the description, this would be a picture of what's going on. We got the river on one side, and we got 3 sides of a rectangle being fenced in. And I think it would be useful if we all labeled this rectangle in the same way. All of these lengths, all 3 of these lengths are unknowns, and so I'm going to go ahead and label them as such with variables. I'm going to say that this side is labeled with an X, this side with a Y, and then this side with a Y as well. You could have used L's and W's, of course. I mean, it's up to you. But I'm going with this. So if you don't mind, let's all go with that. Okay, so now that we have drawn this picture, we need to decide what it is that we are trying to optimize here. And so I'd encourage you to take a minute and look at this right here. It says, what dimensions will require the least amount of fencing if no fencing is needed along the river? So that word least hopefully will make you think a little bit about what we're trying to do here. We are trying to minimize the amount of fencing, and I hope this makes sense why someone would be interested in this. Of course, the less fencing you use, the cheaper it's going to be, probably. But we are restricted by something. We are restricted by the fact that the pasture must contain 245,000 square meters. So let's take a minute here. I want you guys to try to do a couple of things on your own. I want you to figure out what that highlighted phrase means, what dimensions will require the least amount of fencing, and then also the pasture must contain 245,000 square meters. So again, pause the video, try to work with those 2 phrases, see if you can translate them into math from the English that they're written in right now. We'll check it out here in just a second. Okay, so let's deal with the 245,000 square meters first. That is an area concept, and so I'm going to write area equals x times y, right? The area of a rectangle is x times y, and we know that it's supposed to be 245,000 square meters. But it's important to note we are not trying to minimize area. The area has to be exactly 245,000. We are trying to minimize the amount of fencing we need. And my thoughts on this is that when we talk about the amount of fencing you need to enclose like a rectangular shape like this, we're kind of talking about a perimeter concept. Of course, this figure is not completely enclosed by fencing, but I would still call it sort of a perimeter idea. And so I'm going to say the perimeter of fencing is equal to 2y plus x, because there's, of course, 2 y lengths and then the 1 x length. To go all the way around this, you're going to have to pick up the 2 y's as well as the x. And so since we are trying to minimize something, I would say that we are trying to minimize perimeter. Okay, so we're trying to minimize perimeter. Let's think this through. If I'm trying to minimize p, then don't I have to set p prime equal to 0, or perhaps dne? Hopefully you're going there with that. And so I want you to think for a second with this equation that I've got over here, p is equal to 2y plus x. If I were to try to find p prime, I'd have to make a decision. Am I going to find p prime in terms of y or p prime in terms of x? Now, there's not really a good answer to that question. So what we're going to need to do is we're going to have to use the 2 equations that we have here, and we're going to have to use substitution to reduce the number of variables from 3 variables down to just 2. So maybe take a minute, pause the video, and think about how that might work, and show you how it works here in just a second. Okay, so what I'm going to do is I am going to take my area equation, and I'm going to solve it for, I'll solve it for x. So if I solve for x, I'm going to get x is equal to 245,000 over y. So that's really important that I know what to do with this now. That means in the other equation, the one that has to do with perimeter, I can replace any x's that I see with 245,000 minus y. So that would look like this. P equals 2y plus 245,000 over y. I could write it over y, but I'm going to go ahead and write it as y to the negative 1. The reason why I'm going to do that is I know it's going to come next. Remember, if you are trying to minimize p, you're going to have to set p prime equal to 0. So I know I'm about to differentiate. So that's what I'm going to do. I'm going to write p prime equals 2 minus 245,000 y to the negative 2. Okay, so as always, we want to stop and think, is there any value of y that would cause p prime to not exist? And of course, in this case, there is. If y was 0, then p prime wouldn't exist. But I think realistically, for the situation we're talking about here, I don't think that y equals 0 is a part of our realistic domain, because if y was 0, we wouldn't even have a pasture. So I think we can reject that critical number simply based on the logic of the situation in this farmer's field. So what I am going to do, though, is set this equal to 0. We're going to have to do a little bit of algebra to get to where we need to go. So here we go. 2 minus 245,000 times y to the negative 2 equals 0. I've got to deal with that y to the negative 2. And sometimes people will maybe flip this down. Something like that. At some point here, you're going to really, honestly, you're just going to have to multiply through by y squared. So maybe we do that now. That'll make it 2y squared minus 245,000 equals 0. I'm then going to subtract, or I'm going to add, excuse me, and divide. So if I divide 245,000 by 2, I get 122,500. And then, of course, I need to square root both sides. And when I do that, I get 350. Plus or minus, of course, but we're not going to deal with any negative side lengths. Okay, so now that's y equals 350 is a critical number, but we need to prove that this is going to minimize the amount of fencing instead of perhaps maximize it. And so remember from before, we've got two ways to do this, two tools in the toolbox. One is the first derivative test, the second is the second derivative test. And I think that this time the easier way to handle this is actually going to be the second derivative test. So the second derivative test means that we need to find the second derivative. So that would be p double prime is equal to positive 490,000 y to the negative 3. And I'm going to take my critical number and directly plug it in. So p double prime equals 490,000. Actually, let me go back here, sorry. P double prime of 350 is equal to 490,000 times 350 to the negative 3. I'm going to go ahead and calculate that. You can do the same. So I got 0.0114. Important to have the right number, but the most important thing about that number is that it is positive. And so at this point, we can draw our conclusion. So perhaps pause the video here, see if you can write out a conclusion that would go with what we're working with here. And I will do the same thing. Feel free to play the video when you're ready. Okay, so we could say this. Because p double prime of 350 is positive, you could say p is concave up at y equals 350. Therefore, p is minimized at, it should be a 350, sorry, at y equals 350. It did ask for the full dimensions. So if y is 350, we can then use this equation back here for x to tell us what the x ought to be. So if we do 245,000 divided by 350, we end up with 700. So if y is 350, x is 700, and that would produce the minimum amount of fencing given that the area must be 245,000 square meters. Okay, I hope that worked for you. Feel free to rewind the video if you need to, or go back and rewatch it at a later time. But we are going to go ahead and move on to our review questions for 3.7. So if you don't already have those, go ahead and get those out, and we'll start in on those. All right, so here is the first one. This one says, two sides of a triangle have constant lengths A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? And I'll give you a hint here. The formula we want to use for area is area equals 1/2 times AB times sine of theta. So I want you guys to perhaps draw a picture here. I think that might be helpful. But I want you to try to give this one a shot on your own so you can go start to finish. If you get stuck, that's fine. But we want to try to work towards that. So go ahead and pause the video, try it, and push play on the video when you're ready. All right, a couple of really important things for us to recognize and remember here is that A and B are constant. And so they're going to be treated as such. They're not going to be treated as variables. So as we get ready to do some derivatives and things, let's remember that. Okay, so remember what we're trying to do here is we are trying to maximize the triangle's area. So if you were trying to maximize the triangle's area, you need to set A prime or area prime equal to 0 and also consider DNE. I do have this nice formula for area here, so I'm going to go ahead and find A prime, remembering that A and B are constant. So I'm going to get A prime equals 1/2 AB times cosine of theta. Remember that 1/2 AB, just a constant multiple, and so we're going to essentially only differentiate sine of theta, and then we just multiply the 1/2 AB back in there. So that is equal to, that is what A prime is. And we want to consider DNE here. I would say that since cosine theta is always continuous and differentiable, it's always going to exist here, so we're not going to be too concerned about A prime not existing, but we do want to concern ourselves with where A prime is 0. So I'm going to go ahead and write equals 0. Remember on a quiz or a test, writing that down is quite important, so please do. Let's also remember 1/2 AB, simply a constant multiple. So really what we could do here is we could divide both sides by 1/2 AB. And that'll get us down to cosine of theta is equal to 0. So to solve this, we're going to do inverse cosine of both sides. And that'll give me theta equals inverse cosine of 0. So where is cosine 0, or at what angle is cosine 0? We would get theta is equal to pi over 2. It's the only angle that really makes any sense here. Okay, so now we got to decide how are we going to judge whether this is really a max or perhaps it is a min. And we want to use either the first derivative test or perhaps the second derivative test. Up to you on this one. I think I'm going to go second derivative test. First derivative test would work fine, but I'm thinking that finding that second derivative is actually going to be pretty easy on this one. So here we go. I'm going to say that A double prime would equal, well, let's see here, the derivative of cosine theta is negative sine theta, so I'd say that it would be negative 1/2 AB sine of theta. Okay, so then when I try to do my second derivative test, I'm going to be plugging in the critical number, so A double prime of pi over 2 would equal negative 1/2 AB sine of pi over 2, and sine of pi over 2 is 1, and so we'll just end up with negative 1/2 AB, and we know for sure that negative 1/2 AB would be negative. The reason why we know that is that A and B are side lengths on a triangle, so they have to be positive, and so the product of two positives is a positive, and then times a negative will be a negative. So, because A double prime is negative, we can draw a conclusion right now. So I'm going to do that here. Feel free, if you maybe got stuck or something, feel free to pause the video anywhere in here and maybe try to write your conclusion out if you want. So here we go. We will say because A double prime of pi over 2 is negative, we can say that A is concave down at theta equals pi over 2. Therefore, A is maximized when theta equals pi over 2, and we're using the second derivative test there. If you wanted to use the first derivative test and create your intervals and test, it's actually can be a little challenging with the cyclical function like sine or cosine. You want to keep your test values pretty close to your critical numbers, and that's one of the other reasons I think using the second derivative test is better here. That's certainly your choice on that one. Hope that went well. We're going to move on to number 2. All right, in number 2, I'm obviously having a little bit of a hard time fitting this all the way on my page here. It's kind of a tall, skinny graph. Let's go ahead and read it really quick, and we're gonna go back and forth a little bit on this one. This one says, a rectangle is inscribed between the parabolas y equals 4x squared and y equals 20 minus x squared as shown below. What is the maximum area of such a rectangle? And we're supposed to justify our answer. You can see that depending on how you draw this rectangle, it's going to be large or small, tall, skinny, wide, whatever. It's going to take on these different dimensions. It has to be a rectangle, but depending on what those dimensions are, the area is going to be different, and we are trying to maximize that area. So it does say we're supposed to maximize the area, and so if we're trying to maximize area, we need to set area prime equal to 0. But because this area is going to vary depending on how the rectangle is drawn, we need to write out essentially an equation expressing that area relationship, and that's going to be the first thing I'm going to have you do here. So please pause the video, and since we're trying to maximize area, let's write an equation for area. Play the video when you're ready to see. Okay, so to write a formula for the area of this rectangle, of course we need to recognize that the area of a rectangle is base times height. So I'm going to come over here to the picture and try to illustrate that. The base, of course, could be represented by this green line segment that I just drew in there. And again, depending on where that is, like if I were to draw the rectangle up here, that green line segment would be longer. If I drew it up here, it'd be even longer. If I drew it down here, it'd be even shorter. So depending on where I draw it, it's going to, be longer or shorter. So it's going to be a variable expression. And I would encourage you to think about it this way. From the y-axis over to this point over here, I would say that that distance is an x distance. But that x is not enough to express the full base length. Wouldn't there be another x over on the left? There'd be one over here as well. And so I would say that the base length for this particular rectangle would be 2x. 2x. You got that y-axis symmetry, so base length would have to be 2x. Sometimes that's kind of hard for folks to see. Hope that makes sense to you. Finding the height maybe is a little bit easier. Of course, the height, it could be represented by this green line segment right here. And that, of course, is simply the difference between the high function and the low function. And so the high function would be 20 minus x squared. The low function is 4x squared. So I'm going to write the height as 20 minus x squared minus 4x squared. So that right there is the area formula for the rectangle, depending on what x is. And we can do some simplifying here, of course. We could say area equals 2x times 20 minus 5x squared. And then you could distribute and get a equals 40x minus 10x squared. Okay, so now that we got that settled, I want to leave the rest of this up to you. Let's find the maximum area of this, and let's justify our answer as well. So go ahead and pause the video and see what you can do to finish this out and play it when you're ready to see the solution. And now that I'm restarting mine, I see that I made a little mistake here. It's not 10x squared. It should be 10x cubed. I'm sure you all saw that. Sorry for that mistake. Okay, so I think we are good moving forward now. All right, so in order to maximize area, we need to set a prime equal to 0. And we've got a, so to find a prime, we need to differentiate. So I'm going to say a prime is equal to 40 minus 30x squared. And we want to briefly consider, is there any x value that would cause a prime to not exist? And of course there isn't. So we're just going to go ahead and proceed to setting a prime equal to 0. All right, so solving this, we're going to get 40 equals 30x squared. So we get 4/3 equals x squared. And so we'd end up with plus or minus the square root of 4/3 is equal to x. Okay, so let's make sure that this really did produce a maximum area. So we can use either the first or second derivative test. And once again, I think the second derivative test is going to be easier because it's going to be pretty easy to find the second derivative. So the second derivative would be a double prime equals negative 60x. And so since we're dealing with side lengths of a rectangle, I am only going to use the positive side of the square root. I hope that makes sense. Side lengths are never negative. So I'm going to say a double prime of positive square root of 4/3 is equal to negative 60 times the square root of 4/3. And we know for sure that that's negative. So based on that kind of reasoning, we can now draw our conclusion and say, because a double prime of square root of 4/3 is negative, A has a maximum when x equals root 4/3. There we go. Okay, so it did actually ask for what that maximum area would be, and so we've already proven that x equals root 4/3 will provide a maximum area. So to find the area, I'm just going to use my area formula from above. I'm going to say area equals 40 times root 4/3 minus 10 times root 4/3 cubed. So take a second and figure this out in the calculator, and I'll do the same. All right, so using the calculator, I got area would equal 30.792 for the maximum area of this rectangle. Okay, hope that worked out for you. Next up is a little review of some of the connections between f prime, and f double prime. So take a minute and fill out this part coming up right here. Yeah, this part. And when you're ready to play the video and see how these work out, go ahead. All right, here we go. We'll do the first part here. If f prime is positive, then f is increasing. Next one, if g double prime changes sign at x equals c, then g has an inflection point at x equals c. Next one, if h prime changes from decreasing to increasing at x equals c, then h has an inflection point again. Same thing, just defined differently. All right, moving on. Next one says if f prime of c equals 0 and f prime changes from negative to positive at x equals c, then f has a relative minimum. All right, the next one, if h double prime is negative, then h is concave down. And then the last one in this little part, if g double prime of c equals 0, then g has, well, this was kind of a trick. We don't know. You want to say that g has an inflection point, but just because g double prime of c equals 0 does not mean that g has an inflection point. Remember that g double prime actually has to change signs. So g double prime of c equaling 0 might be an important thing, but it doesn't really mean anything as far as the conclusion goes. Okay, let's look at the rest of these. Two more. This one says if f prime of c equals 0 and f prime changes from positive to negative at x equals c, then f has a relative maximum. That's the first derivative test. And the last one, double if there, sorry about that, it says if g prime of c equals 0 and g prime doesn't change signs at x equals c, then g has an inflection point at x equals c. Okay, so this list is in no way exhaustive. Look through your notes, and I think you'll find that there are some others. And if you haven't made some kind of effort to make these connections, you'll definitely want to do that as soon as possible. All right, moving on to our final example. All right, so this one is definitely calculator active. Let's read it real quick here. It says a rectangle is inscribed under the arch of f of x equals sine of x on the interval 0 to pi, as you can see in the graph below. What is the largest area of the rectangle can have, and what dimensions give that area? And we'll work to justify our answer. So we're going to kind of work on this one a little bit together here in pieces. The first thing I want you to do, this is going to be one of the most challenging things about this. I think you're going to find the calculus to be fairly straightforward once we get through this first part. You can see, of course, that depending on how you draw this rectangle, it's going to have different dimensions. So if I drew it here, it's going to look like this. And it's not going to be the same area, same as if I did this. This is still inscribed inside that that sine curve. But it's got different area, different dimensions. So because of that, and we're trying to, of course, maximize the area, we're going to need to write an equation for the area, and writing this equation is going to be probably the most challenging part of this. So pause the video, see what you can do, and then play it when you're ready to see what this area equation would be. Okay, so it is the area of a rectangle again, and so the area formula for that, of course, is just base times height. I'm thinking that you'll probably find the height to be pretty straightforward, but the base is kind of tough. So here we go. I'm going to say that the height is solely dependent on the height of the red curve, right? And the height of the red curve is sine of x. And so I'm going to say area equals b times sine of x. I think my height is going to be sine of x. The base is going to be a little tougher. So let's check that out. If I were to draw in the base, the base would, of course, be right here. And there is, of course, a certain degree of symmetry to this. For example, I would say that this distance right here and this distance right here would have to be the same, because we know that sine of x curve is symmetrical about its high point there. So those two would be the same. And so this is where we're going to start building this. How far do you think it is from right here to, actually, let me switch colors. How far do you think it is from right here over to right here? Of course, it's going to vary based on how the rectangle is drawn, and so since it could vary, I'm going to call this a variable, and I think the most logical variable is x. I think that is an x distance, because x is defined to be the distance from the y-axis over to the right, or perhaps over to the left. And then, continuing on with our idea of symmetry, if that distance is x, then I think this distance over here would also have to be x. So, when it comes time to trying to figure out how long that base is, now of course from here to here, we would do this. We would say that the full length from 0 out there to the far right edge is pi, but to get that base length of the rectangle, I would have to subtract an x and then subtract another x. So pi minus 2x. That would be our base length. So I'm going to come over here and write that down. Area is equal to pi minus 2x, the quantity of that, times sine of x. Definitely challenging, no doubt about it. Hope that makes sense to you, though. So at this point, I think you've got all the tools you need to be able to try to figure out what dimensions maximize the area and what that largest area would be. So go ahead and pause the video and try it and push play when you're ready to see the full rest of the solution. Okay, if we are trying to maximize area, so if we're trying to maximize area, we need to set area prime equal to 0. So the first thing I need to do is find area prime. And I hope you notice this. Area is a product, and so we're going to have to do a product rule as it's currently written. So we're going to go 1 d2 plus 2 d1, and d1 is just negative 2. We always want to consider, that should be a prime, sorry. We always want to consider where a prime doesn't exist, but because all of the functions listed in here are continuous and differentiable everywhere, I don't think that's going to be an issue. But we do want to consider where this is equal to 0, and we want to make sure we confine ourselves to the domain that we're actually working with. And so you might want to clean this up a little bit, but use your calculators to try to figure out what the 0 of this function is, and we'll work with that. So take a minute and do that, and I'll do the same. Okay, so when we calculate the zeros of a prime, we get lots of values. Of course, there are a lot of x-intercepts here, and so I'm going to write a couple of them down. X is equal to, the first one I got was 0.71046. Another one I got was 2.431, and then there's another one out there, I don't know, it's around 5, I think, something like that. But I'm going to stop right here. Of course, there's a lot more, but I'm going to stop right here because based on the realistic domain of this question, not all these numbers are going to work. In fact, I think really only one number works. Let's talk about why that is. We know that from the full distance from 0 out here to the edge is pi. And so if we're going to have a rectangle in there, then these x values really can't be all that large. In fact, the midpoint of our whole interval is roughly 1.5. So I would say anything bigger than 1.5 is actually kind of ridiculous for this particular situation. So I'd say that 2.431 doesn't really even work. So we're kind of left with this as the only option, this 0.71 number. So when you think about that, that's going to allow a rectangle to fit in there, but we want to look carefully at the graph of A prime and notice what's going on at that critical number. And hopefully you're seeing the same thing I am. I'm seeing that at that critical number, A prime changes from positive to negative. And of course, that's exactly what we were looking for, because we were looking to try to maximize the area of the rectangle. And so we can say, therefore, area is maximized when x equals that critical number, 0.71046. So that's great. So I think we've proven at this point that that x value will maximize the area of the rectangle, but it did want to know the area as well as the dimensions. And so take a minute here. This is our area formula right here. And so we could use that, that area formula to calculate what the area should be. So use your calculators to do that. So when I use the calculator on this, I got area equals 1.122 approximately, if you round it off to 3 decimals there. And it does also ask for the dimensions. So we know that the height is equal to sine of x. So if we use our calculators to find the height, we get sine of 0.71046274. So I get a height of 0.652 approximately. And that would also mean we can figure out the base. The base is pi minus 2x. So that would be pi minus 2 times that x value again. And I got 1.72 approximately. So 1.72, I guess if we round to 3 decimals, 1.721. Okay, so I think we've done everything we needed to do. We found the largest area, we found the dimensions, and we did justify our answer using the first derivative test this time. All right, so I hope that went well for you. This video should be posted on your Schoology if you want to go back and watch it for these review questions. Otherwise, I will look forward to seeing you next class. We'll go over your loop quizzes and continue on and finish up with Chapter 3. Hope you've had a good day, and I'll see you soon.